use. When ionization decreases, the critical angle will be greater, the skip distance will be greater, and so will be the dead space. By a simple application of the angles of incidence and reflection, we can also see that skip distance increases when the radio wave is refracted from higher up the ionosphere, such as from layer F1 rather than layer D. Another relevant factor in the refraction of radio waves is the frequency of the radio wave. Because the degree of ionization varies with solar activity, the time of day, and the angle of the sun, the ionized layers vary in their ability to refract radio waves. The highest frequency wave that can be refracted for a given range is known as the critical frequency. Any transmission above this critical frequency will not be refracted, as the radio wave has too much energy for the level of electrons in the layer, and it will pass through the layer. As frequency increases, the critical angle will increase, and the skip distance and dead space will also increase. When refraction does occur, the radio wave may reflect back up to the ionosphere in what is called multi-hop propagation, and this can result in transmissions going halfway round the world. The maximum range for sky waves will be achieved when the path of the radio wave is tangential to the surface of the Earth at both the transmitter and the receiver. However, maximum range may not always be the criterion. Perhaps a stronger signal or a closer recipient may be required. As a consequence of all the factors affecting the ionosphere and the characteristics of different frequencies, the choice of radio frequency is important. Let's work up from the lowest frequency. Low and medium frequencies are absorbed by the D layer, so their propagation as sky waves during the day is poor, and surface waves are used instead. At night, the D layer disappears, and low and medium sky wave propagation is possible by refraction from the E and F layers. This gives them a greater range than by using surface waves. But nighttime sky wave propagation in low and medium wave can interfere with surface wave propagation in the same bands which are used by some navigation equipment, such as NDBs. The high-frequency band, from 3 to 30 MHz, which has a wavelength of between 10 and 100 meters, is the one used for skywave transmission. It is preferable to use the highest frequency possible, because attenuation is less, and this gives the best reception. This is called the maximum usable frequency, or MUF. Finding this frequency is a matter of trial and error, although ionospheric conditions can now be monitored and the MUF can be predicted. It is usually highest at noon, when ionization levels are at their highest. However, because of the inevitable ionospheric fluctuations, a compromise frequency is used, which is called the optimum working frequency. This avoids the possibility of the frequency occasionally being too high and the skip distance being too great. This optimum working frequency is 0.85 times the MUF. Ionization levels are lower at night, and generally the frequency used is half that used during the day. Otherwise, the radio wave would have too much energy and would travel straight through the ionosphere. High-frequency transmissions suffer badly from static interference and are unpleasant to listen to for a long time. So, some equipment is fitted with a selective calling system called cell call. This is a 4-letter code system which enables air traffic control to alert a pilot that ATC wish to speak to him. This avoids the pilot having to monitor his frequency continuously. At the top end of the frequency range, we have very high frequency, VHF, ultra high frequency, UHF, super high frequency, SHF, and extremely high frequency, EHF. Their energy levels are too high to achieve refraction, which limits their range to line of sight. Lastly, in this lesson, let us consider fading, which is the most troublesome problem when receiving radio signals, and it is caused by variations in signal strength because of distance, low transmission power, weather, terrain, and signal-to-aerial polarization matching. Multipath fading occurs when sky waves contaminate surface waves in the low frequency and medium frequency bands. Multipath fading can be overcome by positioning 2 or more receiving antennae in different places, so that at least one will receive a good signal. This is called space diversity. It can also be overcome by using 2 transmitters and 2 receivers, each pair tuned to different frequencies. This is called frequency diversity, and one of the receivers will usually receive a good signal. Let's recap what we have learned in this lesson. Radio waves are transmitted either as ground waves, which can be surface waves, or space waves, or sky waves. The ionosphere is composed of 3 layers, D, E, and F, which is divided into 2, F1 and F2. These layers refract radio waves back to Earth. At night, layer D disappears, layer E almost disappears, and layers F1 and F2 combine. Different radio bands have different transmission characteristics. Long and medium waves are ground waves, but they can transmit further at night as sky waves. High-frequency waves are sky waves, and they are refracted by the ionosphere. And VHF and higher frequency waves are transmitted by line of sight.